Hello, everybody. It is the fourth Sunday of the month, which means we are ready for another episode of Read and Talk About Gemology. My name is Justin K. Prim, and I'm going to be one of the hosts tonight. And we are going to be talking with a very special guest, Dr. John Emmett, coming all the way from Oregon, USA. And we're going to have a pretty, I think, interesting and exciting conversation today. As you can see from our flyer, John was the author of Beryllium, Diffusion of Ruby and Sapphire, among several other articles that we are going to cover tonight. So, Vincent, if you're ready, come on in and we can get a little bit of an idea about who John is and how you guys know each other. Good evening.
Hello, everybody. Yeah, how are you doing?
I'm good. I'm good. It's a calm and clear and cool night here in Bangkok. It's been great weather. Not too hot, not rainy, just perfect. That rare moment of Bangkok weather where it's not too sweaty. So, how is it in your end of town?
Well, in my end of town, it's fine. I had a nice day. We just finished an article today with Pooh and about sapphire from emerald from Madagascar that we sent for the last thing to the editor. So it's a nice day. Easy.
So, what's the story here with John? What's your guys' background together to where you were able to invite him here tonight?
Yeah, the story with John, I decided to invite John because, the first read and talk about gemology last month was with Emily Duminsky. And I explained how, when Emily came in Bangkok and she really helped to set up the data collection and, the analysis of data that we had at GA. Before Emily arrived, we were mainly collecting stone, and then we set up some protocol in order to work on them. But actually, the interesting thing with John is that John was kind of underground mentor, because when I started my career as a gemologist, I studied gemology in Thailand in 2001, and then just at the end of my gemology study, there was a barium treatment that started. And so that was a period where nobody knew exactly what was going on. There was a lot of speculation. And then I went as a gem buyer in Burma. But in 2003, there was this article by John Emmett and many other leading gemologists that really impressed me. And this is one of the very important milestone in my desire to change career and not be anymore just a gem buyer. In Burma, I was buying spinel, but after reading that article, I got more and more interest back to the lab. And then I realized that actually I was not a gem trader, but I really enjoyed gemology. And I decided to move from the gem trade and to be a lab director in 2004. But that article from John was really something that impressed me. And then I say, well, this is what I want to do. This is what I would like to do, trying to find what is going on, learn more about gemstone, and especially corundum, their color, their origin, the treatment, everything about them.
Cool. So I would say he was a pretty instrumental step in your, let's say, life-changing path.
And then when I started to work with GAA in December 2008, then I learned that John was, I knew he was a consultant for the GAA, and he will be the person who will check the quality of the work of everything we will produce. So then that was, okay, so we better do the right thing. And I first met John, I think, in 2012, when I first traveled to the US, to the GA headquarters in Carlsbad. And I was not disappointed. Actually, I was very surprised, because when you deal with John, from the other side of the world, you feel stressed, because you know that if something is wrong, he will just bluntly tell you that this is wrong. But when you meet him, I was thinking, wow, how he will be in real life. And actually, I found out that, he was one of the kindest person I met, but very straight, very straightforward, very kind, very straightforward. So really, it was a pleasure to meet him, and regularly we keep, meeting at every time I was going to the GA research meeting, and I learned a lot from him. And I follow the different article. He follows the different things that we were writing, and it was great. I got a lot of positive inspiration from him. Yeah.
Well, I'm excited to hear some of these stories today. And I know we got to hear a little bit last time with Emily, so now we'll get to hear it direct from the source. So John, if you're ready, come on in. You can unmute and start your video and join us, and we can let the fun begin.
Hello.
Hello. Welcome.
Oh, thank you very much. Good evening to you all. Good morning to people where I am.
Yeah. So yeah, for you, it's quite early in the morning, and for us, it's almost getting kind of late. So we're both in extremes right now.
Right.
So John, let's maybe give a little bit of a summary for anyone in the audience that doesn't know you very well, and just kind of briefly, who are you, and how did you get to this point, I guess?
Well, that's kind of a long story. I grew up in a little town called Rochester, Minnesota, where there's a major medical center called the Mayo Clinic. My dad was a surgeon there, but I was never interested in medicine. I was always interested in physical sciences. And so I went to California Institute of Technology as an undergraduate and got a bachelor's degree in physics. And then I went to Stanford University and got a PhD in physics related entirely to the laser research that my thesis professor was doing. My thesis professor was Arthur Shallow. He won one of the Nobel Prizes for the development of lasers.
Oh.
And so then I got involved with, went to work at the Naval Research Laboratory in Washington, D.C. on very high power lasers, and started developing a lot of the technology for extremely high power lasers. Then a man by the name of Edward Teller, who's a well-known person, I think, in the world because of the development of hydrogen bombs, called me up on the phone and demanded that I meet him for breakfast in Washington, D.C., which was where I was. So I met him there, and he's had breakfast with him. He said, "You've got to come to the Lawrence Livermore National Laboratory and build a laser program for us." And I was 3 years out of school. And the Lawrence Livermore National Laboratory is one of the 2 nuclear weapon laboratories in the United States. Huge place, 12,000 people, sort of like that. So anyway, we argued back and forth for about a year, and finally I agreed to do it. And so I spent most of my professional career developing extremely high power lasers for fusion reactions, to try to use lasers to ignite miniature hydrogen bombs in the laboratory. The idea behind the whole thing was, if you could ignite miniature hydrogen bombs at, say, 1 a second, you could run a whole 1 gigawatt power plant. So that was what was behind it, and also to try to learn some of the physics of hydrogen bombs better. And we built the largest lasers on the face of the earth by a very, very large measure. And that is still going on even after I retired. The last laser they built cost $3 billion to get to some idea of the scale of this thing.
Jeez.
It would fill an area the length of 2 football fields and about 50 feet high and 100 feet wide. I mean, things are that big. Anyway, when I decided, my wife and I collect petrified wood. And so we always went down to the Tucson Gem and Mineral Show. And so we were down to the Gem and Mineral Show, and what we'd do is we'd hit the outside shows, not the big central shows, because that was the same thing every year. But the outside shows were the new people that were coming in and had new things to see. So we'd go hit these outside shows, and we ran into this crazy guy by the name of Sam Spearstra that was mining sapphires up in Montana in the United States. And he had 300 kilograms of rough sapphire that he mined there in 1 kilogram bags that he was trying to sell. And he had a plate full of garnets that came out of the same deposit. And I wasn't very interested in sapphire, but I kind of like garnets. And so I was talking to him to try to wheedle him out of some of the garnets. And I looked at all the sapphire, and it looked like broken green Coke bottle glass, if you know what that looks like.
Yeah.
And I said, I don't know much about this sort of thing, but they said, don't you have to heat treat that stuff, and then you sort it for the best colors and the clearest stones and all of that, and then you take them to Germany to be cut, or to Bangkok or something like that. And he said, I don't want to mess around with that sort of stuff. I like to move dirt. I like to mine. I don't want to do this. And I said, well, I think you're going to have a hard time selling it looking like this. Why don't you at least heat treat it? And he said, do you know how to heat treat it? I said, no. I said, but I can't believe it's too difficult. And he said, how about heat treating it for me? And I said, no. I mean, I was working at the Lawrence Livermore Laboratory at the time, and my job was about 75 hours a week. Okay, that's what that place was like. The organization I had was 350 people. 1,500 people. We had a budget of $350 million a year. I mean, it was a big thing. And there wasn't any time to do anything else. Well, anyway, he would call me up on the phone every 6 months and try to talk me into doing this. And I'd keep turning him down. And this went on for a couple of years. And finally, I decided to retire from the laboratory. I'd been there 17 years and I was just exhausted. And we were having dinner one night, my wife and I, with a very good friend I went to Stanford with by the name of Troy Douthit. And I was telling him about this crazy guy that was mining sapphires up in Montana, and he kept calling me and wanted me to heat treat him. And Troy said, well, let's do it. And I said, Troy, to go out, a furnace, to do this sort of thing, if you really want to have control on everything in the furnace to do something like this is $50,000, $70,000. I said, it just doesn't make any sense. And I said, yeah, you could get a little kiln, but you'd never know what you were doing, And he said, I can build one. He said, you put in 10,000, I'll put in 10,000, let's do it. So I said, okay. And Troy and his partner had a company where they built one-of-a-kinds for the semiconductor industry. When Intel would come up with a new complicated process, then somebody had to build the first machine that fit into a production line, right? Well, Troy and his partner did that. So they built the most unbelievable things. One to go into a production line. And then if it was a process that worked out very well, then one of the big companies would take it over and build 10 or 15 or 100 of them or whatever was required. But anyway, so Troy and his partner had this company that could build almost anything. Vacuum systems, furnaces, just everything you could imagine, atmosphere control systems. And so I said, okay. And in no time flat, Troy had put together a graphite furnace out of parts of old thermal technology furnaces. And this furnace would go to 2,500 degrees centigrade. And it had a ceramic tube down the middle of it so we could, keep the graphite away from the stones and run any kind of atmosphere we wanted through the tube. And so I called up Sam Spearstra and I said, well, send me down 1 kilogram of your junk sapphire and let us run some experiments. Well, anyway, while Troy had been building this thing, I had sat down and sort of started calculating the conditions that we would need to heat treat that sapphire. And that is what temperature, what kind of atmosphere, what kind of time, stuff like that. And so anyway, so Troy had this thing all set up at his this little company he had where they built all these crazy things for the semiconductor industry. And we loaded a kilogram of Sam sapphire into it. This furnace had an inside diameter of about 3.5 or 4 inches and a hot zone that was about a foot long. So it was a big furnace for these sort of temperature ranges. And we put the sapphires in there and we heated them up to temperature. And we started early in the morning, and by the time, we got everything, working and so forth, it was 4 in the afternoon or 5 or something like that. And we ran it up to the temperature, and temperature we started out at was about 1800 degrees centigrade.
Oh.
And anyway, so we sat there and stared at the furnace for about an hour. And one of the things about high temperature furnaces, this is a very, very, very important thing, is there are always 2 thermocouples in high temperature furnaces. There's one thermocouple that's connected to the control system. That the control system you've programmed in the temperature, and so it adjusts the power to make that temperature. Okay. The second is set to a temperature a couple hundred degrees higher, because if the first thermocouple burns out, the controller thinks the furnace has gone cold, so it keeps turning up the power. Well, we only had one thermocouple, but at the time we didn't have another one that would fit. And so we just stayed there and watched it. And we'd watched it for, I don't know, a couple of hours, and we got hungry. So we decided to quickly zip over to a hamburger stand that wasn't very far away and get a couple of hamburgers and come back. We went over to the hamburger stand and we ran into some of our friends there we hadn't seen in a long time and started talking and forgot about the furnace that was running at this place. When all of a sudden we remembered we were racing back over there. And there the furnace was sitting at 2,300 degrees centigrade because the thermocouple, yes, indeed, had burned out. And Sam's entire kilogram of sapphire was liquid, just sort of bubbling away like a teapot. And this much of the ceramic tube that the sapphire is in was liquefied too. And the whole thing was contained in the graphite heating element, just happy as a clam at 2,300 centigrade. So he quick shut the thing down and waited until it was safe, and then went home and went to bed and came back the next day. And we had the sapphire and the ceramic tube was now one gray, solid, opaque piece of corundum. And we had to hammer the thing out of there and we had to break up the graphite heating element and everything. So we made a rule for each other that we would never run a high temperature furnace again without both thermocouples. So that was our first heat treating experiment, and it wasn't very successful.
Yeah.
So that's how we happened to get started at this. And then, go ahead.
When was that? Which year?
Oh, let's see. I think that was 1989, the fall of 1989.
And so what kind of research had you done at that point to figure out those numbers? Were you looking at books or just thinking about general gemology?
No, you have to remember that, my profession was working on lasers. And the first laser that was ever invented was a ruby laser.
Okay.
And made out of a synthetic ruby crystal. And so there had been a tremendous amount of work done on the spectra and thermochemistry and everything of aluminum oxide and a number of other crystals. And so I had a fairly good background in the kind of the physics and chemistry of ruby and sapphire at that point. So I had at least a good idea of where to start. Okay. Because I'd worked with the people that grew the synthetic crystals for the laser business and so forth. And also, aluminum oxide is one of the most heavily studied materials in the world. I mean, okay, so probably there's more research on steel than aluminum oxide, right? And probably on concrete. So if you make a list of these things, of which there are an enormous number of technical papers, I think aluminum oxide would be in the top 10. And so if you actually do a literature search on aluminum oxide or ruby or sapphire or whatever, outside of the gemological literature, there's probably 10,000 papers out there.
Wow. And is that most?
So there's an enormous amount of understanding.
And I didn't really realize that. So what's the rest of the world using it for? Because I know in gem cutting we use it as polishing powder. But what else can you do with it?
Well, first of all, aluminum oxide ceramics are used in all high temperature furnaces.
Okay. Oh yeah, like the.
Okay. Aluminum oxide ceramics are used in all kinds of as mechanical parts in all kinds of things that run at high temperature, or that run in very corrosive environments, or that are in very strong acids, or stuff like that. In addition, sapphire crystals are used for lenses in the infrared and in the ultraviolet. Some of the air-to-air military missiles have sapphire dome front ends on them that their infrared systems look through, and so forth. So it's an enormously important industrial material.
Okay.
I mean, you can buy aluminum oxide ceramic nuts and bolts and bearings and ball bearings and just everything you can imagine.
Yeah.
That would be made out of steel. It's also made out of aluminum oxide ceramic.
Well, I know now as well the iPhone.
Yeah, right there.
Sapphire.
Yeah, exactly. Yeah. And as a matter of fact, an entire huge crystal growing facility was set up down in Arizona and paid for by Apple in order to replace the piece of glass over the whole display with a sapphire piece so it would never get scratched or you'd never break it.
Yeah.
But they could never figure out how to finish the edge well enough so that a crack wouldn't form at the edge. But if it weren't for the edge, you could drop this with a sapphire piece here, you could drop it on a rock and it would just bounce off.
Yeah.
I mean, sapphire is extraordinarily strong.
Yeah.
Okay. At any rate, so yeah, sapphire and the ceramic version of it, aluminum oxide ceramics, are an extraordinarily important industrial commodity in the world. And of course, there's therefore been an enormous amount of research on it. And so there are an enormous number of technical papers. I probably, outside of the gemological world, I probably have 1,000 papers that I've downloaded off the internet and read over the years. As a matter of fact, I don't know whether you can see it, but
I see a big.
Can you see that pile of papers standing over there on the corner of the desk?
Yeah.
Right over there. Well, that's just what I've sort of accumulated in the last couple of months.
That's your COVID reading.
Yeah. No, it's an extraordinary. There's an extraordinarily amount of information out there, and the interesting thing is, gemologists don't read the scientific literature.
No,
they read gemology literature.
Yeah.
Anyway, so that's how we got into it, and the next run was very successful, and Sam Spearster was very impressed. So then he started sending us down a lot of good stuff, and we started modifying the process slowly, and we finally ended up heat treating almost everything he mined, either directly for Sam or for Sam's customers that had bought the material before we started doing this. And it's very difficult material to heat treat. The reason is the titanium concentration is very low, and the iron concentration is quite high, and the magnesium concentration is quite high. And therefore, getting any color out of it is quite difficult.
Okay.
And so we developed a process that has to be very, very tightly controlled in order to get any reasonable value out of what's mined there. And so we ended up then mining that kind of stuff for years and years.
When you were doing the heat treatment from this sapphire, were you checking the chemistry before heating the stone, or you were just guessing based on the color, like burners are doing?
Excuse me, you cut out for just a minute in the middle of your question. Could you ask me again?
When you were doing the heat treatment for the Montana stone,
Yeah.
were you guessing, or were you building your heat treatment setup based on the appearance of the stone, or based on information you had on the chemistry? Basically,
both. You have to remember that you couldn't do very good chemistry back then, and that is the critical things in heat treating sort of colorless sapphire, like Montana sapphire or Sangia sapphire, stuff like that. The critical thing is knowing how much magnesium there is and how much titanium there is, and it's down in the 10 to 50 parts per million range, and making measurements like that are pretty difficult. Although we did make some measurements at the time that Steve Novak did for us in Evans East. Evans East is a big analytical chemistry company on the East Coast of the United States. And he had SIMS equipment, secondary ion mass spectroscopy. There were very, very few of those in the country at the time. And Steve Novak got really interested in what we were doing. And so he analyzed 50 pieces of sapphire for us for all of the low concentration elements. And he did it at about 5% of their going rate because he was interested in it too. And if you'll notice the paper that you've shown on Beryllium, Steve Novak is one of the authors. He did the analytical work for us. And so that's how we knew what the composition was. And once I knew what the composition was, I could figure out what we had to do to get it to turn blue, which is what people wanted in those days, and yellow. Nowadays, people like it the way it is, sort of Coke bottle green.
Because when I started, getting interest in gemology, that was in 1997 when I discovered the book Ruby and Sapphire by Richard Hughes. There was nothing much really about chemistry inside the book. And when I studied at GIA in 2001, there was nothing about chemistry. I studied physical chemistry, but when I started my gemology career, basically there was nothing. And in order to start to understand a little bit about chemistry in corundum, basically I had to wait for your article in 2003. And this is reading the article on the box A and the box B, then I realized about, seriously about the color of corundum, because before there was not much.
Yeah, that's really true. Mineralogy, which is sort of where gemology comes from. Mineralogy has classically studied the composition of minerals, but it has classically studied the composition from the point of view of the major constituents.
Yep.
Now, that's not 100% true, but it's about 95% true. And so there hasn't been a lot of study in mineralogy on the trace elements, which have to do with the color.
Yeah, there were few. There were
few, but not many.
Explaining the origin of color. I met also Kurt Nassau, and Kurt, in his book about treatment, started to, there were some things about that.
Yeah.
And but there was nothing really in depth about corundum.
Mm-hmm. Yeah, that's true. As a matter of fact, you'll notice in that article we wrote in 2003 that we point out there are a lot of things we didn't know about the color in corundum. One of the things we mention in here specifically is that it takes a very, very large amount of iron to get any yellow color at all, when we all used to think that yellow sapphire was colored yellow by iron. Well, mostly it isn't colored yellow by iron. And we point out that we didn't know really how much chromium it took to get a good red, or we only had a rough idea of how much iron titanium pairs. And what doing that whole study and article on beryllium diffusion taught me is that we had no quantitative understanding whatsoever of the color of this mineral. We knew mostly what colored it, not all of them. We got, in that article, we mentioned 5 of the 6 chromophores. We don't address this. We mentioned the 6th one, and that is the trapped hole iron, but we didn't have any way of measuring that one at the time. And it was obvious to me that we just didn't understand this. And so the whole question of color. And so our final resolution of understanding that is the paper that Emily and I and Jennifer wrote. Mm-hmm. And that you talked to Jennifer about on the last one of your not Jennifer, pardon me, Emily.
Yeah.
On your last one of these webinars.
Yeah, that one.
And yeah, that one. And what's interesting about it is what we really had to do to get there. And that is, the first thing we had to do is you couldn't analyze these things well enough. I mean, if you go back to when the beryllium thing first came up, the ability of a gemological laboratory to analyze the stones was essentially negligible.
Yeah.
All they had was an electron microprobe or something like that, and that wouldn't measure those things.
Yeah.
As a matter of fact, you know, when the first, it's sort of a digression, but when the first beryllium stone came up, or the first time that I heard about it, is that it was the end of 2001 or the beginning of 2002. Ken Scarrett called me up and said he saw this stone and it's yellow and it's got this yellow conformal layer on it, and it looks like it was diffused, and what is it? And so he sent me this picture and I looked at it and I said, well, obviously it is diffused. And I said, given that color, it's probably diffused by a very light element that's alloyvalent with aluminum. That is, it has a different valence than aluminum. Okay, yeah, that's a good picture of that layer around the outside. Okay, what does alloyvalent mean? Aluminum has a valence of 3, yep. And beryllium has a valence of 2, and say lithium has a valence of 1. Okay. And I knew that it had to be an element with a valence less than 3 of aluminum. Okay. And that's from understanding the defect structure and what the crystal would do to try to accommodate this thing that had the wrong valence. And so I said to Ken, I said, well, it's probably beryllium or magnesium or lithium. I said, I think it's more likely magnesium or lithium, because I would be very surprised that people would deal with beryllium, which is an extremely hazardous material. And of course, yeah. And of course, that's what it turned out to be. But I'm coming at this from the point of view of a scientist, where beryllium is something we have to deal with fairly often, and it's extraordinarily toxic. Beryllium hydroxide is extraordinary, the toxics, and gives you a disease called berylliosis. And so I just didn't imagine that anybody with a backyard furnace or anything would be stuffing beryllium into it. But what they were doing was not stuffing beryllium into it. They were stuffing ground up chrysoberyl into it, which is relatively safe. But then after they used up all the chrysoberyl around, they started using beryllium oxide powder, and that is very dangerous.
Yeah, as a matter of fact, I heard, you know, when the burners and people found out that actually it was barium that makes the treatment, and then you can get oxide, you know, in the trade, and you didn't have to buy chrysoberyl and turn it into powder. I heard that burners started to work with barium oxide, and several people died.
Yeah, I can believe it.
At this time, the burners in Chandanbury, many burners were basically heating stone in the, you know, in the house, maybe in the cellar or in the garage or things like that. And you know, they were heating, and then the vapors were going around, and several people died and were intoxicated. And since then, most of the burners are doing now heat treatment on the roof,
Yeah,
where it's well ventilated. But I heard 2001, 2002, 2003, 2004, discussing with people, I heard that several people died.
Yeah. Well, that's why I didn't think it was beryllium at first. But anyway, how we learned it was finally beryllium is that we're still in January of 2002, and Shane McClure calls me up on out of the clear blue sky and said that they've seen one of these stones. And I said, yeah, Ken sent me these pictures. He said, yeah, Ken sent me the picture too, and so forth. And he said, we got one of those stones and we cut it in half, and we could see the orange layer on the one we had. And he said, we took it up to Caltech and ran it on their X-ray fluorescence equipment. And the composition in the orange layer is exactly the same as the composition in the pink layer in the center. So we don't understand what's happening. And I said, well, first of all, it's a light element. And second of all, the concentration is probably not more than 20 or 30 parts per million. And I said, the instrumentation that Caltech has and that most geology departments have will not measure that low concentration of a light element. So I said, what you've got to do is you've got to go to somebody that has SIMS, and the only one I knew in the United States was Steve Novak's at Evans East. So Shane got on a plane and flew back to Evans East, and Steve ran the measurements on, and we were all down at Tucson at that point in a GILC meeting. And I had gotten up and explained what I thought it was and everything, and other people from other gem labs had gotten up and come up with crazy explanations as to what it was, you know, things like that. And then Shane comes into the meeting, and he just got back from Steve Novak and said it's beryllium. We measured it. So that's how we knew it was beryllium. Up until that point, I wasn't sure which of the three light elements it was.
Okay, so that kind of gives us an idea about how it became known in the lab side. But Vincent, you also have a bit of the story of how it actually started to happen in Chantaburi as well, right? From the burner side, I mean.
Yeah, well, from the burner side, he told me that, you know, the burner who discovered the treatment was called Mr. Tai, and he was involved in a heat treatment of yellow sapphire in Chantaburi that was discovered by another burner who actually, he also, you know, he was experimenting with a new furnace. He had an electric furnace in the 1980s. He was experimenting with a new furnace, and he had several gas bottles, and he fell asleep in front of the furnace. He was not going to a shop in order to buy. He fell asleep, and then one of the gas bottles became empty, and then the atmosphere became oxidizing, and he was heating around 1007, 1008. And when he opened the furnace, all the stones were bright yellow. So the name of the burner was Samuel Kewen, and this is the way he discovered how to heat yellow sapphire at high temperature with electric furnace and oxidizing. And Mr. Tai was one of the suppliers for Samuel Kewen. So Mr. Tai was going to Sri Lanka and he was bringing back stone in Thailand, but he was not a gemologist. And so he was buying stone, in parcel. And then, back and forth, he decided to start his own experiment. And one day he found out that, when he was hitting sapphire with another stone that was slightly different, the results were much better. And so he started to find these stones and select them out. He learned how to identify, and then he was turning them into powder, and he was eating his sapphire with the powder of that stone. And he was doing that. He told me he started doing that in 1993, around 1993. And it is, so he worked for nearly 7 or 8 years with Sri Lankan sapphire. And then one day, some people bring him sapphire from a new deposit in Madagascar, in Ilakak, and there was a kind of tutti frutti of stone with different colors. And he did a test with his technique using barium powder, and the stone became all color, super bright. He was hitting some pink, some purple, everything together, and he gets some very interesting result. And this is the way he started. So he just started. He told me that he discovered that because at the beginning he didn't know that all the light yellow stone were not corundum. He was thinking that everything was corundum. He was eating everything together. And then there was some problem. But his observation skills were good enough to be able to identify that, actually, the stones are not all the same. There is this one, they are different from this one. When I only hit the sapphire, it's not so good result, but when there is the two together in the furnace, I get good result. So he discovered the thing in a totally empiric way. And he told me at this time he had no idea that there was barium in chrysoberyl. And he learned that when he heard, from the gemologist that, there is barium inside chrysoberyl, that's why. So he learned from, and he became a big fan of everything that John is publishing. John will tell you later about that. He became a very big fan of John because he said, "Yeah, this guy has a good ideas." I like what he's doing.
That's funny. The interesting thing about all this is we knew at the end of that GILC meeting in 2002 what it was. Okay. But we couldn't convince anybody in the gem labs that's what it was. Okay. I mean, it's really, really, really an interesting situation. I mean, what Trey and I did then is that we, people wouldn't believe it. GIA wouldn't believe it. They wouldn't, when they had one of these stones, they wouldn't write a report saying it was beryllium diffused. And the reason is what is it? The Thai
Gem
and Jewelry Association of Chanterbury or something like that was saying, no, they weren't doing beryllium diffusion. And the government was backing them up saying, no, they're not doing, beryllium diffusion. And GIA wouldn't write a report. Other labs were still saying, it's iron 4+ or, just crazy stuff. And so what Troy and I did is because of the heat treating, we had a lot of different kinds of samples of stones. By this time, we were heat treating material from all over the world. And so what we just did is we just beryllium diffused a whole bunch of stones. First, what we did is we set up a diffusion experiment where we used beryllium oxide, and one where we used powdered chrysoberyl, and one where we used powdered beryl.
Mm.
Okay. And we ran all these things. We ran them up at 1800 degrees for, I don't know, 30 to 100 hours and so forth. And they all work fine except the beryl. And I'll explain that later if we have time. But anyway, and so then we took a sample of all the different kinds of stuff we had. We beryllium diffused them. And that's what all those pictures are in the article. Maybe you want to show picture, say, 29.
Okay.
Okay, so the stuff is on the left. We have mine run material from Ilokaka, Madagascar. And you can see there's colorless stuff and there's pink stuff and there's bluish stuff and so forth. And after beryllium diffusion, you can see that there's orange. The blues are lighter in color. There are some that are still pink. There's some that are, still colorless. But anyway, there's a whole bunch of color there. And one of the problems with convincing people at gemological laboratories that this was beryllium diffusion is because they kept thinking that beryllium had to make one color because they had no understanding whatsoever of color in the stone. I mean, all of these things happen because beryllium makes a trapped hole, and the trapped hole reacts with different trace elements in the stone to make all those different colors. It's not beryllium that makes all those different colors. It's the trapped hole. And the trapped hole is an oxygen ion that instead of having a valence of -2, has a valence of -1. And that's how the charge compensation is done. And that's why there's so many colors, because the trapped hole can either associate with the beryllium or can associate with the iron or can associate with chromium or it can associate with nickel or whatever. So this is why you got all these colors. But because they have no understanding of what made colors in the first place, they just couldn't deal with the fact, none of the gemological laboratories could deal with the fact that all these different colors were coming in. And show me picture 28 now. Okay. The stuff on the left is from King's Plain. It's typically the very dark blue to brown, very high iron content sapphire. And you look at it after diffusion, and they're colorless stones and they're yellow stones, and the remaining blue stones are a much lighter color in blue. Okay. So you say, wait a minute, one thing can't do all those different things. Okay.
Actually, barium is a poison for blue. That's what I learned from your article. It's a poison for blue. It kills the blue.
Yeah. And so that was the difficulty. And I mean, GIA, pretty much had the same problem, and that is all the way through 2002, they were really, really unwilling to say, okay, these are beryllium diffused. I mean, even though there was a SIMS measurement showing that's what it was, the difference, all these different things that this one thing beryllium does was just too hard to get your head around. Anyway, so we went all the way around, and Troy and I did this with every different kind of stone you could imagine, and provided people samples, and it just didn't make any difference because it wasn't possible for me to make a scientific explanation that a person with no scientific background could judge the validity of the explanation. I mean, that's not unusual. I mean, there are a lot of areas in science where I'm not an expert. And if somebody tells me all about it and I ask a question and he gives me, a complicated answer, I can't judge myself whether it's right or wrong. I have to take his word for it because he's the expert on that area. Well, they had the same problems. They were an expert on gemstones, but they weren't an expert on the defect chemistry of crystals. And so they couldn't judge from their own experience whether what I was saying was right or not.
I guess
I'm not critical of that, but that's the way it is. What?
There was no instrument at this time to be able to prove that, oh, this stone color is coming from barium or not. We were mainly working, I was not in lab at that time, but they were mainly working with microscope. Some lab had chemistry, but it was EDXRF, but not all the lab chemistry. And they had UV visible or maybe FTR, and that was it for most labs.
Yeah, I have to compliment GIA on, and that is Tom Moses and Ken Scarrett, even though he's still at the AGTA lab at that, I think at that point, came out to my house and said, we've got to be able to analyze this stuff. We've looked at SIMS and it's far too complicated. And so I recommended that they invest in laser ablation ICP-MS, because that, back then you could get a facility set up for about $350,000, and a SIMS facility was like $2 million. And also, it was my judgment that a SIMS piece of equipment was just beyond what a gemological laboratory could manage effectively. It's very, very, very complicated equipment. And so Tom laid out the $350,000, and I got a laser ablation ICP-MS machine, and then we could start analyzing things. And then it became a little bit more obvious.
So this is like a kind of an important moment in gemological history whenever you kind of go from the old way to what's now the new way, right? Like advanced gemology began at that moment when they got that LA-ICP-MS. That's really interesting.
Then the other part of that is we get all the way around to 2003 now, and we're having the GILC meeting, although now it's broadened quite a bit. And they've invited people from the major jewelry places like Tiffany's and the French company's name escapes me at the moment, and so forth, to the meeting. And it was really amazing. First of all, I was on first thing, and I stood up and explained this as clearly as I could. And then a man got up from the TIRE, the Chanterbury Gem and Jewelry Association, and said, absolutely not. The ties are not beryllium diffusing these stones. It's absolutely not true. And then there was just sort of everybody sat there, they didn't know what to do. And finally, the woman from Tiffany's, who was a colored stone buyer for Tiffany's, and unfortunately, I don't remember her name right now, but she got up and said, Tiffany's wants the Thai Gem and Jewelry Association, or whatever the name of it was, to know that Tiffany has no need to buy corundum gems if they don't know what they are. And she just sat down. Nobody said another thing, and the meeting broke up. And 2 weeks later, they announced that, yes, indeed, this was beryllium diffusion. So all of the research we did, all of the fancy equipment, all of the tests and everything we ran didn't really make any difference, because nobody could buy into what we were saying until somebody started to take the money off the table. And then all of a sudden, everybody became converted, and ties admitted what they were doing. It was a very, very interesting meeting.
That shows the interest to have a meeting with people from different backgrounds.
Absolutely, absolutely.
And with, one speak about science and the others don't understand, but when there is one person who speaks about money in the middle, maybe everybody understands a little bit. What does it mean?
Yeah, that was really interesting.
Okay, we have a problem. Oh my God.
So then what happened was about 4 or 5 months after that, I got a call from Shane and no, it was from Tom Moses saying, we can't let this happen again. And we've got to start to understand this stuff. Would you teach a bunch of our people the background of all this kind of thing? Because, you know, what the ties do next, we have no idea. And we can't go a year and a half like we did with this thing without being able to get our hands on it. And so I said I'd try. And so, you know, Shane and a bunch of other people came out and I started trying to teach this stuff. And we tried a couple sessions and it didn't work. First of all, they were too busy. And second of all, every simple little thing that's scientific or every simple little calculation is something they had no background in. And so it was almost impossible to try to explain things when they didn't know what a formula meant or various physical ideas and how you calculate things and stuff like that. So we kind of dropped it, and somewhere along the line there, Ken moved to GIA.
Yeah.
And after he'd been there for a while, he called me up on the phone and said, I really think it's necessary that this kind of science be taught to some gemologists. And he said, how do you think we ought to do it? And I said, well, why don't you take some of your young people? You know, you do have some young people that do have some technical background, you know, whether they just have a bachelor's degree in chemistry or biology or whatever. But why don't you find a group that's sort of young and learning gemology and has some scientific background? And so he put together a group of 6 people, 2 from Bangkok, 2 from New York, Tim Thomas, who was working for them here in the Portland area, and 1 from Carlsbad. And they met at my house for weekends, and I would lecture the entire weekend. And then they would fly back to Bangkok or New York or whatever. So, and we did this every month or every other month for about 18 months. And I put together the lectures and tried to teach them all the very fundamental things and how all this goes. And those lectures are probably 900 PowerPoint slides today. And it was very difficult to do because we'd start to talk about something and all of a sudden one of the simple assumptions of it were things they didn't understand. So then I'd have to go back and in the next lecture, I'd have to teach that stuff. So we would go 2 steps forward, 1 step back, 2 steps forward, 1 step back, all through this 12 months. And then what I would do is I would assign homework they had to do. They had to make some measurements in the lab, or they had to calculate some things, or they had to guess what, if you put silicon in, what it would react with or something. And so then what I had them do is I had them come and they all presented their homework first. And we'd go through and talk about that. And then I'd do the next set of lectures and so forth. And I don't know how well it taught them, but it really taught me. I mean, I really began to understand this far better than I'd understood it before. There's nothing like having to explain it to somebody who's asking questions. You know, that was a lot of fun. Karen cooked lunch for everybody, and we had a woman who's a friend of ours that catered dinner here at the house because we're a long way from restaurants and so forth. So we really had a lot of fun. I really enjoyed doing it.
So Emily was one of them, and then in Bangkok you have Kai, who is still Bangkok. Kai
and Ren Lu, who's now in China, and Nathan Renfro, who's in Carlsbad.
And Vishen.
Yeah. And Tim Thomas, who worked for GIA then for quite a while and is now back working at Applied Technology, or Applied Materials, I think it's called. I think GIA, or the gemology world, only has 3 of the 6 I taught.
I think now 2 are remaining at GA. There is still Nathan in Carlsbad, and Kai is in Bangkok. She's leading the colostomy
Yeah.
department.
Yeah.
All the other one are gone. Emily went, on her. She went for a master. She left GA and she went for MBA, and then she went. Now she's a designer.
Yep, indeed.
And Ren and Andy are now back in China. They are at Wuhan University.
They're spread out all over the place. Yeah. Well, anyway, I don't know if it really made a technical contribution to gemology, but I certainly learned a lot teaching the course.
Well,
I mean, really.
In Bangkok, it did, because when Kai and when Wood were coming back,
yep.
They were putting all this PowerPoint, in the computer, and the system was other gemologists were, told that they should read about that. And we had, sometimes we had some discussion. I went to discuss quite a lot with Wood about that. And we discussed quite a lot, and I also learned a lot as, second wave type of learning. I was reading this thing, and it really helped even more when Emily came in Bangkok, and for nearly 1 year, she was busy with dealing with fabrication, trying to make sure that our fabrication was correct. So there was, the signal we are collecting, the spectra we are collecting, were really checking the material, or not some internal reflection, some wedge, some reflection, some particles, and things like that. So everybody in Bangkok, all the people in data connection, learned a lot from that.
Oh, and yeah, I know they did, and they do it very well.
On chemistry.
Yeah, they do it. They do a very, very good job.
We're not allowing our article to go out,
Yeah. Well, one of the things we did in this class is we taught people how to take decent spectra. And that is, I have these mounts that I've used since back in the 80s that we put the little wafers in. And I had designed this gadget that allows you to optically orient the stones and so forth. And in the course of this, because Tim was involved in this course, he is one of the best optical engineers optomechanical engineers I've ever met. And he designed up mounts that were much better than the ones I'd built, and got them installed in the equipment that GIA used. And then he had my sample holders made in quantities of hundreds, so that they could all put those things in. And he made a much more professional version of the optical alignment tool. And he figured out a way to make it align biaxial stones as well as uniaxial stones. Mm-hmm. So those got built for all the laboratories, and all of this was sort of a part of this course we were doing. And so in addition to sort of upgrading the understanding, we were upgrading the instruments that the laboratories had to use to make the measurements and so forth. So, facing what we couldn't do and didn't know when Beryllium hit to where we are today, the ability of the laboratories to make measurements and to fabricate samples and everything is really profoundly improved. And the starting of your activity to collect stones in a valid way from all different places of the world, that just meant it was possible to have stones that we knew what they were, and with the laser ablation equipment, we could analyze them, and with the spectroscopic setups we installed in the laboratory, we could take good spectra. And then it became possible to start to really make some conclusions. The next problem we faced was how do we calibrate the laser ablation ICP well enough?
Mm.
And that's a difficult situation because what you end up having to do is subtracting this element from that element to see what's left. And so you got to make the measurements accurately. Okay. And so I talked to Tom Moses, and if we could start a major effort to develop some standards that could be used with laser ablation ICP as those really accurate standards. And he assigned Tim Thomas to work with me on that. And that became a rather long effort. And that is, Tim started, got it about halfway through. He left to work at Applied Materials. And Jennifer Stone Sunberg took it over and drove it all the way through, so that we now have ion implant standards in corundum, in high purity sapphire for each trace element. And we have used those to calibrate corundum crystals that we grew with all those different elements, and grew large crystals so that we could do it very uniformly. And those all are cut and fabricated individually, calibrated against SIMS at Caltech, and then those go to each one of GIA's laboratories. And so we can make really precise measurements. And
that was super important, because what many people don't realize is that GA has one problem that many other labs don't have, is GA had 5 facilities. They had 5 labs, one in New York, one in Carlsbad, one in Bangkok, one in Tokyo, one in Hong Kong, while most of the other lab has only one lab with one instrument. So they never had to do, the same testing on different instruments on different places. But for GA, the idea that you check a stone in one lab, you get one result, and then you check the stone in another lab and you get another result, was something very scary. So there was really a very strong interest into making sure that developing protocol in order to make sure that the results that we get in Bangkok will be the same in New York, or will be the same in Carlsbad.
Yeah.
So, yeah, that was really something.
And let me tell you, it really was expensive. First of all, you had the salaries of the people at GIA that were working on this involved, and then we had to grow about 10 crystals that cost us $15,000 to $20,000 a piece. And then we had to calibrate all those. And then we had to make ion implant standards, and I forgot how expensive that was. And then we had to use days and days and days and days of SIMS time at Caltech, which we had to pay for, to calibrate the standards, and then actually went in the lab, calibrate them against the ion implant standards that we calibrated by SIMS. And I mean, it was a real undertaking. If I'm sure there's probably well over $500,000 that GIA spent to be able to put first-rate standards in all 5 laboratories, and to maintain the calibration of all those 5 instruments to do it. I mean, it is an enormous undertaking. And the fact that Tom Moses signed up for that and knew how important it was is really impressive to me.
And also the side effect of that was, when this new standard came, all the data collection we did using all the standards and before and things like that, basically we had to do it again.
Yes.
So you imagine that, okay, you have some new standard and they cost this much, but now all the data collection work we did, so the salary, the time, and the time spent on the instrument, and the salary of the people that were doing the work before, now do it again.
Yep.
That was
The big job. Big
yeah,
job.
big job.
Okay, then once we had all this in place, and you were collecting stones from around the world,
Yeah.
it was possible to figure out exactly how strong each one of these, to identify, first of all 6 chromophores, and then to figure out exactly how strong they were. That is how many parts per million it took to get some color. And we found out that the range and strength of those things was a factor of 1,000.
Yeah.
And that is, it takes 1,000th the amount of iron trapped hole pairs to make yellow as it does iron. 3,000 parts per million of iron will make about the same amount of yellow as about 9/10 of a part per million of trapped hole pairs. And anyway, once we could do all of those things right, we really went in and understood all the chromophores and calibrated them. And that's the paper that you talked about with Emily. Emily did all the color calculations. Jennifer did all the standard measurements and getting everything calibrated right. And also Jennifer managed the growth of we had to grow synthetic crystals with just one chromophore in each one to validate the measurements we made on the natural ones, which had a couple of chromophores, generally in each one. And so she managed the growth of all those crystals to do that too. So
on the process, you include silicon inside.
Yeah.
Was believed, like most gemologists were thinking, oh, silicon is not compatible with corundum, so there is no silicon in corundum.
Right. Well, but there is. Yeah.
That was the knowledge, let's say, around until 2003.
Yeah. Well, let me tell you, when Steve Novak made the first SIMS measurements for me back when we were first starting to heat treat, silicon was one of the elements that he found. That's how I knew it had silicon.
Yeah.
Yeah.
But most of the gemologists are from a geology background, and they say, oh, corundum form when there is no more silicon. So there is, and the instrument that we have, don't detect silicon. So, the dogma
if you can't see it, it's not there.
Yeah. Exactly. If not, it will not be corundum. It will be another mineral. So there is
right.
And of course, and basically, cool silicon have an influence on color. It was basically the same if you were starting to speak about aliens. If you started to say, what would be the impact of silicon on color?
Right.
Yeah.
Well, anyway, so the interesting thing about all this is if you take the beryllium paper and the silicon and sapphire paper and the quantitative determination of the chromophores and corundum paper, that's all part of what started because of the beryllium diffusion problem. Yep. We understood a lot of the beryllium diffusion problem, but if you read that paper carefully, you'll notice that I wrote in there were quite a number. I pointed out quite a number of things we didn't understand yet. Okay, and essentially what we finished up with this last paper is we now understood the things in the original beryllium paper that we didn't understand.
Yeah.
So it's sort of taken a long time, but we finally got there.
15 years. But and still, because there are some color centers that are still not explained. There are some sapphires, they have some colors that we still don't really understand. This unstable color center that when you take it to the sun, the color gets stronger and then the color gets down. So it's incredible because there were these 10,000 paper on corundum, and we don't, and we realized with this barium treatment that actually we don't know that much about color in corundum. So this gentleman in Canterbury, with playing with his chrysoberyl and doing his treatment, put gemology basically upside down, and thanks to him, there was suddenly the need, and they found the resource in order to work for basically 15 years on color in corundum and trying to understand what is going on. And that was great. And also the field gemology program, because the reason why GA started the field gemology program was not to, okay, let's make a field gemology program to work on origin determination. That was not the goal at the beginning. The goal was, let's build a field gemology department to make sure that the sample we collect were not heat treated before. So we can do some experiment, we can work on this sample, and we know they were not heat treated. So we will be able to work on this treatment determination. And the side effect was, okay, we have now an instrument like LA-ICP-MS, and we found out that when we work on corundum from this place, actually LA-ICP-MS is kind of useful or very useful for origin determination. We found that actually it's super useful for emerald, and for rubies kind of powerful, but for blue sapphire it's a kind of complicated. But all these things are actually the consequence of this heat treatment with barium.
Yeah, they are. All of the stuff we do came from that.
Yeah.
Well, of course, you can understand how important it is. I mean, one of my friends who's a gem dealer in Japan told me that the Japanese bought $100 million worth of this beryllium diffused Quad-Paracha sapphire before they found out it was essentially worthless. So yeah, I mean, it made a big impact on a lot of people.
But gemology was super lucky to have, a kind of retired physicist, scientist, who was available and who had the right knowledge and also the right connection with these people in this lab in order to say, okay, let's have fun and let's work on that.
And isn't that rather amazing? I mean, speaking of random happenings, I mean,
Justin, you are still very young, but can you imagine that, one day you get retired and then suddenly there is a treatment happen, and for the next 15 years, you will go to work on that. And before you were doing lasers, and then you try to find a way, oh, actually, we don't know too much about the origin of color in corundum. Let's have fun about that and find out the role of silica. And by the way, what is this stuff with iron? Iron 2, iron 3, what is it doing? You see, your plan from retirement was dictated by a guy in Canterbury playing with corundum and trustable and finding out a way to change color, and it changed your life.
Yep. It's really very interesting. But you have to understand, I'm the sort of ultimate nerd. I mean, I've had a lab in my home since I was 5 years old. Okay, I mean, it's just today it's a very different lab than it was when I was 5 years old. But I have a rather extensive laboratory in my home. Yeah. The only thing I don't have is a laser ablation ICP-MS machine, which is unfortunately is not a casual use instrument. It's something that you've got to dedicate people to and use and keep calibrated and so forth. Yeah. And so, the group in Bangkok has been very, very nice to me by analyzing samples I've had and so forth, and also loaning me the samples that they've characterized and run the spectrum on and so forth. But I mean, this is a hobby of mine. I mean, I'm 81 and I'm retired. What would I do? I mean, sit and watch television or something? I'm just fascinated by a million of these things. I mean,
I think you were kind of a hammer without a nail, and then suddenly you see, oh, there is a nail there. Okay, let's do some work. Have some fun.
I think
Yeah.
one thing that's really cool about the story that you just told us, and this kind of goes back to really the spirit of this, the theme of this webinar, but also what we were talking about last month with Emily. You know, you read an article in a magazine and you're like, okay, that's interesting, but you don't really realize, like, for instance, what we were talking about last month, like that article took 10 years to write. And now we find out with the beryllium diffusion article, like, okay, $250,000 had to get spent to build all these different machines to calibrate all this stuff before you could even start the project, really, right? I mean,
Really?
so much stuff had to happen just for a 10 whatever page article. For us it's just a magazine article, but for you it's like, or for the team, it's like such a huge thing that
It
you
really is. I mean,
can almost not imagine
you-
what's behind these.
yeah, you have no idea what's behind it. Oh, here's the table of the analysis of this stone. What you don't realize is that, maybe $750,000 got spent to get to the point where you could take the data to put in that little table.
Yeah.
I mean, yeah, it's really remarkable.
You see,
Yeah,
one of the things I learned when I was collaborating with John when I was working at GIA, and what I was very impressed is his way to handle problems. We went one day to do I think that was the first time I collaborated with John on something. We went with Sky, like, okay, let's be motivated. We went to Chanterbury in order to do an experiment about heat treatment with barium for blue sapphire with the burner who found the barium treatment. And we decided to do, we decided that during the week, gave a call to the burner. The burner, we went to his place and with our equipment, and then we came back and we were super happy, like, the normal gemology stuff. And then we sent a photo of the before and after to John. And John look at that, John look at the thing and he say, what is that crap? Because we were enthusiastic, but we didn't prepare our experiment correctly. So basically the photographs were done with 2 different lights, with 2 different backgrounds. So basically the whole experiment was useless because we wanted to compare a before and after, but we didn't, started the first thing like thinking, okay, what we want to do, what should we do, what should we prepare before to do that? And this is exactly what John told us. He said, that was bad because you didn't prepare. You didn't put yourself first what was the right question, what you want to show, and make sure that your demonstration will be clean. Yeah. So this is what you have to do, and say, oh my God. And then we end up buying this huge camera. You remember, John? The camera with the axis?
Yeah, that was a copy of the one I had in my lab. Yeah.
Before and after, and put them in the database because you found out that, the color calibration of the photograph was not done even correctly. And then you teach us with this small gray circle, how to calibrate the photo correctly and how to make sure that all the photos are stored in a format that will be correct for colors. That was amazing. And when I saw that, I say, okay, now I understand. Okay, when everything is in the preparation, you have one problem, stop, think, and then act. When I was doing diving, and then the diving instructor were telling me that there is a problem, you stop, you think, you act. I was remembering that, okay, that should be maybe John Emmett motto. Stop, think, and act. I don't know if you want to, but that was that. And that
that's what you learn being an experimental physicist. And I've been an experimental physicist all my life. And after, the first time you find out your measurements are worthless, you really, after you spent 6 months on something and you found out that your procedure wasn't worth anything and the data was just junk and you have to start over from scratch. After that happens to you a time or two, you really learn the discipline of experimental science. I mean,
John,
it's hard work.
John, one thing I wanted to know, because you were talking about this Corundum 101 class you were doing, and your 900 slides. Have you thought about putting that together as a book for gemologists who want to transition into more scientific?
Yeah, actually I did. What we were going to do is Emily Dubinsky was going to take the responsibility to essentially take the slides and write the book. And that is, the slides are not standalone. The slides were done with me standing there explaining it. Okay.
Yeah.
And so Emily was a particularly adept student in this class because she has a master's degree in materials science from Stanford. And so we decided that she would do that, and then I would do all the editing of it. And then she found the situation at GIA not very supportive and not very to her liking, and so she left GIA. And frankly, I don't have the energy to write a book at this point in my life.
Okay.
So that's why it didn't get done. Otherwise, it would have been done some years ago.
Yeah. Okay. Well,
Jennifer was a tremendous loss to the world of gemology because she had the intellectual capability, the background, and an enormous amount of energy, and she could really make things happen.
Well, we had a few questions from the audience, so maybe it's a good time to go through some of those.
Okay.
So this one's from Mubashir Mansour. First of all, he said he's a huge fan of your work, but he was wondering, what do you think on the potentials of computational material science and quantum chemistry, such as density functional theory, on heat treatment optimizations and electronic band structure calculations of sapphires for the purpose of the gem industry?
Oh, the last bit for the purpose of the gem industry. First of all of that stuff is being pursued to an enormously detailed degree in the world of science and chemistry, and that is there are many very complex simulations of every defect, every impurity that you could possibly imagine in the corundum lattice, and so forth. That's being done. I would venture that half that pile of papers on the corner of my desk deal with that in oxide crystals, including corundum. First of all, there's an enormous amount of that calculation in every kind of semiconductor in the world, and then in a whole bunch of wide gap semiconductor materials, and then in a whole bunch of wide gap oxides and so forth. Now, as to what that will do for gemology, is it will simply inform us as to what defects are energetically more possible than other defects and things like that. So there's a lot of that work. There's a very large amount of that work being done, but it's really beyond the ability of the people at GemLabs to even read the papers, I would say. With a few exceptions.
Yeah.
But it's the literature I follow very closely. It's the literature I started following very closely when I was at Livermore, because one of the things we did was develop a lot of new laser crystals. As to whether that finds its way into gemology, other than the limited explanations I provide in these papers we write about the defect chemistry, I'm not sure.
Do you think is it important for gemology to understand this, or is there a reason why this is outside of their realm of expertise?
Oh, well, the reason it's outside of their realm is because they don't read literature outside of gemology.
Yeah. Maybe.
I would say that probably very few people in gemology laboratories have the educational background to follow that. When you get into that sort of things, when you get into numerical simulations of crystal structures where you're calculating the detailed equilibrium of 300 atoms in a crystal or something like that, that's something that you probably pretty much got to be. I mean, you can understand what the conclusion is, but if you want to be critical, you have to be an expert at that field, and that is very, very, very specialized work. And if you're doing that kind of work, you're at a major computing facility somewhere in the world, and so forth. I would say that I am not able to be intensely critical of the comparison of all of these different numerical simulation techniques. Okay. So it's sort of beyond what I can be critical of, because I'm not a computer programmer and I haven't run these simulations and I don't know what the limitations are and the various myriad of assumptions that go into them and so forth.
Yeah.
And so basically what you have to do is just look at papers that come out every few years where the work of the previous year has been improved or corrected and so forth.
Yeah.
But no, I don't think, I think very few people in the world of gemology would be able to follow that, or that it would have immediate interest.
And
See, you have in gemology, most of the people who work in a gem lab have a bachelor degree. Some of them have master. Now, slowly and slowly, when big lab are hiring people, they're hiring now people mainly with a master degree or a PhD or a postdoc.
Yeah,
yeah. 20 years ago,
20 years ago, it wasn't like that at all.
Nobody went to university. Very few people even went to university. So and actually this is the way why I was able to move to a gem lab, because when I started collaborating at the AGS, I found out that I was the only one who studied chemistry in university. None of the people at the AGS lab went to university to study science.
Right.
So suddenly, when I arrived there in 2002, 2003, 2004, when we were speaking about spectroscopy, at least I studied that in university and I had a background. So I was able to deal much better with this instrument than any other people at the lab, because they didn't have the basics.
Yeah. It's changing. I mean, there are much more highly educated people in material science related issues coming into the gem labs now. I think 5 or 10 years from now, it'll be a very different world.
And there are some people who read, because there are some people, they never studied science, but I can tell you they read. And two of them, Ken Scarratt and Richard Hughes, I can tell you that it's not, they never went to university. Ken was a former military, and Richard went to traveling, but they are people who read. So, over
absolutely
practice and
well, it was Dick that let me publish the first Beryllium experiments and explanation on his website. And he gave us the first opportunity to write our studies of the color and the chromophores in the current version of his ruby and sapphire book. And he let me write it the way I wanted to write it, which I greatly appreciate.
Yeah.
Okay, so we got another question. This one's from Mark Langston. He's asking, is the key factor with LA-ICP-MS being so valuable due to it showing the full periodic table and fingerprints of the trace elements?
No, let me just explain something. First of all, laser ablation ICP-MS can't show you the whole periodic table of elements because there are masses that interfere. And that is, in laser ablation ICP-MS, you vaporize the stone and ionize the vapor, but it's in an argon atmosphere. And there's always hydrogen around, there's always oxygen around because, you know, parts per million. And so molecules form, and the molecules go into the mass spectrometer. And so, for example, you can't measure silicon with the kind of laser ablation ICP-MS machines we have today, simply because there is an interference with one of the, I think it's argon hydrogen +1 or something like that, that interferes with it. And so there's a lot of data in the literature that shows the silicon content of corundum to be 500 to 1,000 parts per million, and it's not there at all. And that's the interference, and that's because people just use these instruments rather than validating it. When we made the ion implant standards, we made an ion implant standard for silicon also, to see what the instrument could measure and what the interferences were. Okay, and you know, an instrument like a laser ablation ICP-MS, I mean, at the Lawrence Livermore Laboratory, which I worked, we would have a team of people that spent their entire careers with those, making measurements with those instruments and making better calibrations and understanding interferences and everything like that. And gem labs just don't have that depth, and most universities don't either. And so there are all these papers out there with laser ablation ICP-M measurements that show a horrendous amount of silicon in it. And if it's there, it's 25 parts per million, it's not 800. So, yeah.
Ray gas, you cannot check. Yeah.
So then what is making it so important and so valuable for the research? I mean,
well, okay, what is making so with any instrument, any kind of an instrument will make a measurement. Any kind of an instrument has limitations. The most important thing about using scientific instrumentation is to understand the limitations and use it where it's valid and not use it where it isn't valid. Okay, we get a tremendous value to the origin determination of these stones by measuring a series of trace elements, which are not 100% of all the trace elements in corundum, but they're most of them. And most of those we have proved we can measure with great validity. Okay. So yes, every kind of a measurement you make has its limitations.
Okay.
And you have to understand the limitations as the first thing you need to know before you start taking data. So.
But LA-ICP-MS is basically an instrument that enables you to have, you know, some quantitative, reliable quantitative data on some elements that are interesting to gemology. Basically, that there was EDXRF that is semi-quantitative, but doesn't work with all the light elements.
Right.
So basically, with LA-ICP-MS, we can now work in a gem lab with a light element, and barium was especially barium, and the sensitivity is good enough to be able to find out if you know, you may have in some corundums corundums that contain with natural content of barium, and you can find with LA-ICP-MS all the other trace elements and be able to separate the stones that were heated with barium and the stone that has maybe nanoparticle that host barium.
Yep,
so
absolutely.
LA-ICP-MS is a very useful instrument on that point of view. It doesn't solve all the problem. As John say, we cannot get silica, fluorine, rare gas. There are many things we cannot get, but there are also several things that we could not get before to get LA-ICP-MS.
Yeah. Well, let me tell you something else. With regard to corundum, and this is not emerald and everything else, but with regard to corundum, with laser ablation ICP-MS, we can analyze every element that is relevant to what we need to know except silicon. Okay. And we can measure it down to a part per million level. And given the strengths of the various chromophores, 1 part per million is an adequate measurement. So the only thing we lack for corundum right now is silicon. And Jennifer is currently evaluating a new type of machine, a new type of laser ablation ICP-MS machine that runs in an entirely different way. And she's taking some of our standards and some of our samples to see if this new technique can measure silicon. Okay, so we're continuing to work on the problem.
Okay.
But the laser ablation ICP-MS right now does almost everything we need for for corundum, and is quite adequate for emerald, for example. Okay,
it's very good for emerald.
So no, this is a giant step forward for gemology. I mean, it really is.
Okay.
This is not to say we can't do better. 10 years from now, we may even have something better.
Yeah.
But it is so far beyond what we had when the beryllium hit the world. It's just day and night.
Yeah.
Better than what the world was then.
Okay, so another question from the audience. Can you please explain about the beryllium treatment to intensify blue color in corundum?
It doesn't intensify it, it reduces it. Would you please show, what is it, 29 or 30 is it?
30.
The 3 pictures side by side?
Yeah, I got it.
Yeah. Question from Sutas.
Okay, yeah. Okay, so this is a wafer that's 9/10 of a millimeter thick, and it's cut out of a very, very dark sapphire from Shandong, China. And the first picture to the left is the wafer, and it's sitting on a light box. And so it's photographed in transmitted light. And it's a very, very, very dark blue. Okay, so what we did is we diffused beryllium into it, and you'll notice some of the blue areas completely disappeared, and the various very dark blue areas in the sample are much lightened. Okay, so the yellow areas in that stone are the fact that the beryllium, the trapped hole, completely washed out the iron titanium pair there and left a trapped hole coloration, which is just yellow. We then heated it in a reducing atmosphere so that trapped hole, so that charge compensation is not provided by a trapped hole, but it's provided by an oxygen vacancy. And the end result is the yellow color goes away, and that stone now is a very, very pale blue. You remember it's 9/10 of a millimeter thick and sitting on a light box. If you were holding that in your hand, you'd say that's a pretty good blue color in C, but it's being lit very brightly from behind for comparison. And so that is one way to do it. Now there's another thing you can do, and that is you can essentially use beryllium to wash out the blue, and then you could rediffuse a small amount of titanium into it and put blue back in and put it in more uniformly. So there's a bunch of manipulations you can do, but this gives you some idea what's involved.
Yeah.
John, you know that this figure is the way the burner who developed the heat treatment with barium was able to develop the heat treatment of blue sapphire with barium. Because he read your article when there was a meeting, and I remember I was in the meeting, and the burner came, and there were people from different labs, and people asked, "But by the way, how did you found a way to heat treat sapphire with blue sapphire with barium?" And he said, "Well, I read the article, 2003 by John Emmett and everybody, and then there was this slide, and with that slide, I understood that barium actually was a poison for blue, and then all the stone that the geodas that became too dark after heat treatment, there was a way to reduce the blue without the stone to turn green, without the yellow to come." So he figured out about that. So basically, what many people, and I guess that was what Sutas was asking, is how you come from a stone that is milky, geuda, milky, colorless, and you turn it after barium as a perfect blue. It means, burners, they do a heat treatment. Everything that is too dark, they will make a second step heat treatment with barium in order to bring it to the medium blue.
Yeah.
And
Well,
green will not come.
Yeah, I should have not published this figure because I wasn't trying to make the problem worse. I thought people were probably doing that, and so I just wanted to explain it. And when Ken invited me to come to Bangkok and give a lecture, I met the guy who has been doing this, and he said, "Thank you for writing that in the paper. It taught me how to lighten that dark blue sapphire." and only then did I know they learned it from me rather than me explaining what they were doing. So I made a mistake on that one. Figure surely shouldn't have been there.
Well, at least, with that paper, the good thing with that paper is you get people like me, and you get people like him, and many people, getting some benefit about reading a good paper about gemology, and people see, their point in a different part of the paper. But, well, this is the essence of a good paper. It's a paper that has a consequence and make people think and make people willing to experiment more and to learn more.
Yeah.
So it was great that you did that.
Well, let me just explain one thing. Once you understand what each one of these chromophores are, and once you understand where every one of these impurities energy levels are in the band gap, you can look at a problem, say lightening a dark blue sapphire, or taking this sort of purplish ruby and making a pigeon blood ruby out of it or whatever. You can start understanding exactly what you have to manipulate, and you know what all of the pieces of the problem are. And so you can tell immediately whether in principle that's something you could do to the stone or not something you could do to the stone. So, for example, let's take the example of some of the rubies or pink sapphire that you occasionally see that has yellow areas in it. Well, it's pretty easy to understand how to get rid of the yellow area in it, and that is the yellow area is caused by a trapped hole. And the way to get rid of a trapped hole is you either diffuse some hydrogen into it, or you create an oxygen vacancy. So that's sort of an example. So anything you want to do, you know what the tools you have are. You can add trapped holes, you can subtract trapped holes. You can add oxygen vacancies, you can subtract oxygen vacancies. You can add titanium, you can cancel titanium with magnesium, et cetera, et cetera, et cetera. Now, some of these things may be too slow to do in the laboratory, and some of them may be very, very easy to make work. so that you can't practically do everything you can conceive of, but you can do most of it.
Mm.
Well, metamorphic yellow sapphire, people know how to do that for 1,000 years, for more than
Yeah.
1,000. The
Yeah.
blowpipe technique turned light blue sapphire and a light yellow sapphire into colorless,
Yeah.
and a purplish stone into pink, because
Yeah.
basically blowpipe is removing the blue. You remove the blue, and basically you make the stone kind of, you remove an absorption, and the stone is lighter in color.
Yep. Yep. Most of that is covered in Alberuni's book that was written in 1040 AD.
Yeah. He was not speaking about trap hole.
No, he was not speaking about trapped holes.
But people in Sri Lanka were, and even maybe before, you just imagine that people, the first miners, maybe 5,000 or 6,000 years ago, they were eating things, they had sapphires, they were around a fire, and they put something in the fire, and a few days later, they come back to the fire, and why is slightly different compared to before? So probably heat treatment of corundum is maybe as old as mining corundum and people enjoying time around a fire and something like that. So it's...
Well, let me give you an example. I mean, suppose you were living back in 800 AD or 1000 AD or something like that, and you just conquered this group of people and you wanted them to pay you a ton of gold, all right? How do you know that the gold was pure? You didn't have a laser ablation ICP-MS machine, and maybe they put a whole lot of silver and copper into the gold so that it wasn't, so nearly expensive to pay you this tribute. So what did they do back then? You know what they did?
They bid it?
No, they heated it with salt. They heated it for days and days and days with salt at roughly 1,000 degrees or something like that. And the chlorine in the salt combined with the silver and copper and vaporized out of the melt. And by that simple technique, they could take very, very impure gold and make it about 98% gold.
Wow.
I think that is so cool. They had no idea how to make the measurement to tell them what it was, but they had a good experimental method of making pure gold out of whatever it was.
And that's so weird. You have to just wonder what would have, led them to put salt into the gold. How did they figure that out? That's just so weird.
I don't know, but I'd sure like to ask the guy who did it.
Okay, so a gold mine near the sea, and they were eating. They were cooking with fish with salt, and then they said, okay, about the gold, and then they found out, there is a little bit less than before. What that? And
well, yeah, look, it's exactly the same thing as discovering the piece of chrysoberyl that was sitting next to the piece of sapphire that you heat treated and turned it orange. It's having the ability to be a good enough scientist to observe something that you don't expect.
Yeah.
I mean, the guy that did that, a really, really smart and a really, really good observational scientist. And no question about that.
Yeah.
I agree.
So I guess we can wrap up with one last question.
Okay.
It is maybe kind of obscure, I think. It's again from Mubashir Mansour, who, by the way, he was saying before that DFT on sapphire defects is his PhD thesis topic, so he really appreciated your comments about that. But now he's wondering your opinion on Punsiri technique. He says he can't quite get his head around that.
The problem there is that as I'd have to go back and look at that. I wrote that all up in the in the Corundum 101 course. But I think the situation there is, as the furnace cools down, they probably turn off the hydrogen and enough oxygen seeps in to decolorize the room. I'd have to go back. In this course, we calculated that out and plotted the curves of just the way it would cool down to decolorize the room like that. And I just don't have that at my fingertips here.
Okay.
But it's very straightforward, and it's a complicated calculation, but we did it in the class. It was probably the most difficult thing we did in the class, but as a matter of fact, I had to do it twice to explain it well enough.
So maybe
again, the technique was is done with
It's not. It was obviously. It was obviously not done intentionally.
yeah, no. It's, I think it's done with mainly sapphires that are rich in magnesium, and it's a multi-step. And again, Mr. Punsiri never studied science. He was met him several times. He was grown up on a coconut plantation, and then he went to a pilgrimage in Kataragama, and on the way back, he stopped in Ratnapur and he saw the gem trade, and he decided to start doing that. And because he was a farmer, he played with, chemical for his coconut and things like that.
Yeah.
And then he decided to, he learned the technique from the ties, and he has very good observation skill, and he's very well organized. Another thing, like if you observe well and you are very well organized, then, there is something different. But because you set up your thing correctly, then you can find out the reason why. And so I'm not surprised that this is a person like Mr. Punsiri who was able to find this treatment technique that works only with some type of corundum.
Yeah, some type of corundum is right. Before we close, I'd like to make a request,
Okay.
and that is the following. When I wrote the Beryllium diffusion article, I spent a few pages at the front of it writing the history from the point I got involved. All the crazy things that happened before we, so forth. And one of the things I've gotten from talking with you is gotten the Thai side of how they got to where it was that I got involved. And I think it would be really, really interesting if you would write a paper on the history of how all this evolved up to the point where the Gem Labs got involved in.
I did that. Actually, that was one of the first paper I wrote, but I did that in French for the French Gemological magazine about the history of because I went to interview all the different burners, and I was fascinated, especially after reading your article. I went to meet all the burners, and I wanted to know their side of the story. So I went to meet Mr. Tai, I went to meet Sam Wonke Wen, and when I went to Sri Lanka, I went to meet Mr. Punsiri. And I wanted to know their side of the story and how they got involved and how they discovered that. So I wrote that about the Thai burners for the French Gemological magazine in 2005, 2006. But it is in French.
One of my problems in life is I only understand one language. And I just am extraordinarily envious of people that are multilingual. But unfortunately, I'm not. The high school I went to, the only other language they talked was Latin.
Actually, about that, speaking about that, there are several articles in Thai, because there was some meeting in Thailand in around 2004, 2005, after the thing where you had people, burners, who came and they explained their side of the story. And I think it was the Department of Mineralogical Resources. And they publish a kind of book about that. But sadly, it's not even in English, it's in Thai. So
No.
you have the story of Samwon Kewen. You have the story about Mr. Tai for the barium.
Mm.
You have also inside Jonk speaking about borax on how the ties were able to,
Yeah.
they found out how to heat rubies with borax. And you have also the leg glass, but it's in Thai.
Mhm.
And actually, I asked my wife to translate the article so I could, based on this work, I was able to write the article in French.
Mhm. Well, I wish somebody would put that all together in English while the people that participated are still alive.
I think there is an article about that was written by Terry Coldham, but not about the barium side. It was basically the Geuda side, but for the barium, yeah, maybe.
Yeah.
No, we
Okay.
can work on something.
Maybe we
All right.
need to find some time to do an English translation for us non-Francophiles.
Yeah, could be done. Could be done. I have to find somewhere to publish it then.
Yeah.
Mm.
Could be done. Could be done.
Well, I don't think that would be difficult. I think Gems and Gemology would be quite willing to publish a historical article. The other thing I think is that new journal that Ken's putting out from the ICA lab would
Gina?
really appreciate an article like that.
Mhm.
Now, unfortunately, I'm not the one that makes a decision for either one of those, but those are certainly two things I would think about.
Yeah.
Well,
I particularly think the ICA thing. What do they call it? Gamma or something like that?
Gina.
Yeah. I think it might go particularly well there.
There is a very simple way to do something like that. Is next time you speak with Ken, you tell him, why don't you ask Vincent to do something like that? And then Ken will come to see Vincent, John says that he will be interested about something like that. And then, I never say no to John, or I never say no to Ken.
Well, let me also tell you that Ken and I have a standing Zoom call on Saturday night here. Okay. And either he's busy or I'm busy about half of the time, but so every couple of weeks we end up talking, and I'll raise the issue. The last comment I'd like to make is I appreciate all of your support and all of the samples and all of your encouragement and all that you've done to make the determination of origin of some of these stones valid. It's a great contribution.
Well, I would not have been able to do that if there was not a crazy physician moving into gemology and starting to pick up my interest. And I owe that to you. People like you and Ken and Richard Hughes. I was so happy to be able to do that because, when you do something, when I go around in the field, the most important thing for me is I like this to be useful to something. So I don't want the sample to stay somewhere, on some shelf and nobody to do anything with them. So I feel that when somebody can work on this sample and turn them into something useful, I feel much more motivated, to go to the field and to collect more stones. So
very good.
It's
valuable.
No, I appreciate, and I all the time appreciated all your, comment and concern about that, because at the end I was feeling that every time I was speaking with you, I was growing up.
Mm-hmm.
And okay, we have to start again, no problem. And next time, and we were doing better. So I thank you for all your, how do you call that? Editing and advising and encouragement. It was great.
Most people call it criticism.
No, but your criticism, every time it was constructive, because you were criticizing, but then you were saying, if I was you, I will suggest you do this and that. So you never put on any other thing that we did. I never saw that you say this is bad, and when you were not proposing a way to improve. And every time we learn, and then we learn how to do the thing correctly, and then we grew.
Mhm.
So it was very useful. It was really really very useful. There are many things that I will never do anymore because, yeah, now I understood why it was bad and basically useless. Remember, you told me that I think we can. For me, you are the person who told me, Vincent, there is only one thing that is worse than no data. It's bad data, because if you publish bad data, people will use it and then there will be confusion. And this is exactly what is going on these days with internet and with all the social media. Nobody knows anymore where there is good data because you have so many fake news and so many bad data everywhere that nobody had any idea about what is real and what is fake.
That's true.
Well said.
Yeah.
Okay, John. Well, I just also want to thank you so much for giving us a couple hours of your time and being our guest and telling us such really interesting and really important stories. You know, I think for maybe many of us, we haven't heard some of these stories, and I love the idea of thinking about, you know, this transitional moment in the history of gemology, you know, because of the beryllium treatment and because of what you guys were discovering as a reaction to what the tie burners were doing. It's just, you know, it's really something that's going to be in the history books whenever the history books get written. It's you know, it's a crucial moment in time. So thank you so much for sharing that with us. It's so cool.
Hmm. Well, thank you so much for the conversation. I enjoyed it too.
And
Thanks,
so,
John. Really appreciate it.
and for our guests, John is not really on social media or doing too much, but, you know, online, obviously he's busy doing too many other things. But yeah, I guess if you need really to get a hold of him, maybe if you need some of those scientific equations, maybe you can go via Vincent or something. But of course, Vincent and I are on social media active. And if you guys missed any of our past webinars, you can follow that little bit.ly link, and all of the ones we've ever done since February are up there. Next webinar is going to be November 22nd. Do we have a guest yet? Do we know?
Yeah, sure. We have a guest.
Is it a secret?
Next month it will be. We are going back to gemology with hand tools. You know, when I went to study gemology in Burma, it was in 2000. I went with 3 books. There are 3 books that really motivate me to learn. And I went with Ruby and Sapphire by Richard Hughes. I went with the 4 Atlas of Inclusion by John Coivula and Dr. Gublin. And then I went with a small book that was called Gem Identification Made Easy by Antoinette Matlins. And we are going to speak with Antoinette about this book and about basically the instruments that you can have, the pocket instruments that you can have in the field. And in maybe 99% of the case, you can identify the stone if you have, let's say, 3 or 4 pocket instruments and a brain full of useful knowledge.
Great. So yeah, I know she was at a lot of our. She was a watcher in a lot of our older talks. So it'd be good to actually get her up in front of the camera and front and center. I'm sure she'll have a lot to tell us. So okay, that'll be great.
And this book is probably one of the most successful book about gemology ever, with possibly the book by Walter Schumann. You know, this one and the other one are probably, there is maybe 6 or 7 editions of this book. So I went with one of them and then I just love it. And thanks to that book, I was able to buy with confidence, with kind of good confidence. I learned how to buy sample in a market like in Burma or, you know, anywhere around the world. Because you know your instrument and you know the limitation of this instrument. exactly what John was saying. Even with a simple instrument, it can be useful or it can be a disaster.
It's true.
Yeah.
Okay, guys. Well, I think we have said what we need to say, and I think we're ready to sign off here. So thank you, John. Thank you, Vincent. And hopefully, John, we will see you sooner than later once the world has regained some sense of normality. We can all have dinner sometime.
I would really enjoy that.
Me too.
Yeah. Thanks, John. Have a nice Sunday.
Okay, same to you. Bye-bye.
You
Goodbye.
guys.